Welcome to EPG Pathshala in Computer Science. So, we are looking at a series of lectures in computer networks. So, we will be looking at multicasting today. With respect to multicasting, there are two important protocols. One is the DVM-RP protocol and the next is the PIM protocol. So, we had already looked at the DVM-RP protocol. So, today we will be looking at the PIM protocol or the protocol independent multicasting mechanism. There are different modes of operation in PIM. One called the dense mode of operation, another called the sparse mode of operation. We will take a look at both these modes of operation, and we will also look at how PIM is used when you have multicasting to be done across domains. For internet where you have multiple domains in operation, and when you have the multicast members spread out across various domains, how is it that this PIM related multicast will work. So, these are the things that we will be looking at in today's lecture. So, just a brief on multicasting as such. We know that multicasting is there to facilitate group communication. There are a number of usages of multicast. There are many applications which use it. For example, transmitting news, stock price, software updates to multiple hosts, multimedia teleconferencing, multiplayer games, distributed simulations and so on. And with respect to routing for multicasting, the problem statement can be given as follows. You can say that the goal is to find a tree or trees which are connecting the routers having local multicast group members. So, when we talk of a tree, it could be either a shared tree, which means that the same tree is used by all group members, or it could be a source based tree where each source will have a different tree, right. So, that is when you have each sender sending to the same members, a different tree would be formed because which has the root at that particular source. So, we had already looked at a source based tree, which is a source based tree kind of protocol, which is DVM-RP. So, what we will be looking at now is a shared tree protocol, which is the PIM protocol. So, when you look at PIM or protocol independent multicasting, the name itself kind of says what is expected of this protocol. So, this protocol independent term here essentially means that it is not dependent on any specific underlying unicast routing algorithm. It works with all underlying unicast routing algorithm. This is unlike DVM-RP. So, DVM-RP on the other hand works only with the RIP or the distance vector based unicast routing algorithm. So, in that sense PIM is considered to be protocol independent because it does not depend on any specific unicast algorithm. And there are two different multicast distribution scenarios that PIM considers. One is called the dense mode of operation. So, in the dense mode of operation, we are looking at a situation where the group members are densely packed in, that is they are all in close proximity and there is plenty of bandwidth available. Since you have plenty of bandwidth, you can have multiple redundant transmissions also that could take place. So, that is what happens in the dense mode of operation. In the sparse mode of operation, the number of networks with group members is small with respect to the interconnected networks. So, you kind of can look at it as a situation where the group members are widely dispersed and bandwidth is not plentiful. So, in these cases we look at it as a sparse mode of operation, that is we have fewer number of members, but they are spread out across various networks. So, this is a situation where we use a sparse mode of operation. We will look at both these in detail now. So, if you look at this dense sparse dichotomy, what are the consequences of that? So, if you look at the dense protocol, the dense situation, so what we do in the case of dense membership is that group membership by routers is assumed until the routers explicitly prune. Remember that we talk about pruning messages, right. That is when a tree is constructed, if a particular router does not belong to that tree, that is it does not have any members, it will normally, that branch can be pruned, right. So, the routers will normally explicitly send prune messages. We have looked at an example of, we looked at how this works when we talked about the DVM-RP protocol. So, dense PIM basically works like the DVM-RP protocol in the sense that it uses a flood and prune technique. So, in this case it is assumed that all the routers have the group membership until the routers explicitly send a prune message. So, you can say that this is kind of a data driven construction on the multicast tree and it uses the RPF reverse path forwarding technique, and bandwidth and non-group router processing is a little extra in this. That is, you are using additional bandwidth and processing by non-group routers also is done additionally. So, these are some overheads that you have in the dense protocol. If you look at the sparse protocol, this is kind of different when compared to the dense protocol, in the sense that there is no membership until the routers explicitly join. So, in dense we assume that everybody is already a member, whereas in sparse we wait for members to explicitly join the tree, or join the let the protocol know that there are members here, that they are interested in receiving the data. Also, you can look at this as a receiver driven construction of multicast tree. Okay, it is a center based construction, and bandwidth and non-group router processing are conserved. Okay, it is a conservative approach to the bandwidth and non-group router processing. So, that is the difference between these two. So, if you look at the details of the PIM dense protocol, so as we said, it basically uses a flood and prune technique, flood and prune and reverse path forwarding. So, similar to DVM-RP. The only difference with respect to DVM-RP is that the underlying unicast protocol provides RPF info for incoming datagram. It could be any underlying unicast protocol. Second thing is that it is less complicated in the way it does the downstream flooding when compared to DVM-RP, and it reduces reliance on the underlying routing algorithm. So, specifically what PIM does when compared to DVM-RP is that it will forward on all its ports until it explicitly gets a prune message from one of the links, from one of the ports. So, in that sense it is a little less complicated than DVM-RP. It has to maintain less amount of state. Also, it has a protocol mechanism for router to detect if it is a leaf node router, so that it can inform the higher nodes, the higher routers appropriately, or the upstream routers appropriately. So, let us just look at a quick example of the flood and prune technique as it is used in PIM-DM. So, let us say Mary has some data that she wants to send to a group G1, which consists of members John and Bill. So, assume that we have a network like this. So, we have Mary here connected to R6, John is connected to R4 through R2, and Bill is here. Okay. So, now let us say for instance, so Bill and John also want to receive messages from this. So, they will have to inform their respective designated routers, their first hop routers, that they are interested in receiving this message. So, I want to receive message from G1. This information is given by Bill to R3, which is its designated router, and this will be done through IGMP protocol. There is no effect of PIM in this. Okay. So, Bill would have informed R3. So, R3 knows that it would like to receive messages from G1. Similarly, so let us say John also wants to receive messages. So, he wants to receive messages from G1. So, he informs that to R4. Okay. So, now what happens is when Mary sends the message, she sends it as a multicast datagram, and that is sent to R6. And what does R6 do? It just floods it along the other ports that it has. So, it is sent to R3 and to R2. Now, similarly, now R2 will flood it to R4 and R5, and R3 will again flood it to R1 and R2, and so on, right. And finally, through the flooding mechanism to reach R4, reach R3, therefore it reaches Bill. Now, remember that you can see that in addition to reaching the desired receivers, it is also being sent to other routers which are actually not interested in receiving this data. Okay. So, Ram for instance does not want to receive message from Mary. So, now R1 therefore will have to, since R1 does not have any members who are interested in this group, it sends a prune message to R3. Similarly, Bob also will not be interested in receiving any message from this group. So, so this router here R5 also does not have any members, therefore, this will also send a prune message. So, once the prune messages are sent, you can see what will happen. So, the final tree is constructed with R6 connected to Mary, and then R2 and R4 to reach John, and through R3 you can reach Bill. So, once the final tree is constructed, you have the sender here and the receiver here, and Mary can now continue to send data. Now, you can see that since these other branches have been pruned, the data is not unnecessarily transmitted along other paths, but only to the necessary receivers. Okay. So, now Mary can send all the messages to Bill and John. So, this is basically how the PIM-DM mechanism will work. Okay. So, you can see that data is being sent from Mary to both the receivers. Okay. Next is the PIM sparse mode of operation. So, in the sparse mode of operation, the approach is slightly different. So here we are looking at a shared tree, so which means we would like to have one common shared tree which is used by all the members. If it's a common shared tree, then we need to have one common root, right. So, so we can say it's a center based approach, and that root that we talk about for the tree is what is called as the rendezvous point, so or the RP. So typically what happens in the sparse mode is that the router will send join messages to the rendezvous point, and all the intermediate routers will update the state and forward the join. So they keep forwarding the join until the join will reaches the RP. Okay. So after joining via RP, the router can also switch to a source specific tree. So this option is also there in sparse mode. There is normally it will work in the shared tree mode, but you can also have a source specific tree mode. That is, we will look at shortly at how in detail how that will happen. Okay, this is provided, this option is provided in order to increase performance, and so that you can have less concentration of paths and you can have shorter paths. So if you look at, so typically if you look at R6 as their rendezvous point, and if R1 and R3 want to receive data, so they would be sending join messages to R6, and all the data will be sent from R6 to the down the tree to R1 and R3. Okay, this is basically how the sparse mode of operation will work. We look at the details now. So what are the senders expected to do? So once the RP rooted tree has been constructed, the sender will unicast the data that it needs to transmit to RP. Okay, so once it goes to RP, the RP then will distribute the data down its tree. So the RP can also extend the multicast tree upstream to the source, that is also possible, and it can also send a stop message if there are no attached receivers. There is no one is listening, then RP can send a stop message to the sender so that the sender does not unnecessarily send any of these group messages. Okay, so this is the these are the basic ideas that are used in the PIM sparse mode. So the RFCs related to this are 2362 and 4601, which give the details of the PIM SM protocol. Now there are certain terminologies that we need to remember with respect to PIM SM. DR, which is the designated router, and RP, which is the rendezvous point, which will be the root of the tree, and RPT is the RP based tree. Okay. Now the PIM SM process can be looked at as working in three phases. Okay, the first phase is essentially the construction of the RP tree and sending the data through this RP tree. Phase 2 is what is called as a register stop message, process, and the third phase is called as the shortest path tree. Now this is an optional phase, okay, but most all PIM SM based multicast routing will involve these two phases, RP tree and register stop. So let's look at the RP tree phase first. So what are the various steps that need to take place here? Basically it starts with the receiver joining the group and informing the RP that it's basically interested in receiving messages. So the receiver basically starts with sending a join message to the designated router using IGMP protocol. So the IGMP is our group management protocol. So IGMP protocol will be used by the receiver to inform its designated router. Remember, the designated router is the one that it is directly connected to. Now the DR then is part of the PIM protocol. So the DR, the designated router, will now send a *G PIM join message saying that whoever be the source, it is interested in joining this group. The star here essentially refers to the fact that the source is wildcarded. Anybody could be the source, but as long as the destination address is the group address, is the multicast group address G, then DR is interested in joining that particular group. So it sends a PIM join message to the RP. Now this RP or the rendezvous point is kind of elected to be so, and this election process is outside of the PIM protocol. So you can look at it as being assigned as one of the routers in the entire domain, being assigned as the RP. So everybody knows who the RP is. So the DR knows it can send the PIM messages to this RP. Okay, so that's our assumption. Now this PIM join message will either reach RP or it will converge on a router on the RP tree. That is, if there is already some other DR, router has already sent a message, and this message also goes to the same router on that path, then this message that is being sent need not really go all the way up to the RP, but it will stop at that particular router. So it converges on an intermediate router. And this join message is also sent out periodically, otherwise it will time out. And what do we expect the sender to do? the sender will send a packet with multicast address at its destination to DR. Now look at this, when the receiver has, when multiple receivers are there and all of them have sent their join messages, you know that a tree has been constructed up to the RP, that is routed at the RP, from the RP to all the receivers, a tree has been constructed. So now all that the sender has to do is send the packet to the multicast address as its destination to its DR, to its designated router. And what this designated router will now do is, it will now unicast this packet, that is it will encapsulate this multicast packet into a unicast packet and send it to the RP. Okay, this is called as a PIM register packet. So it sends what is called as a PIM register packet to RP, and what the RP now will do is, it will decapsulate that packet that it is getting, that is it decapsulates that unicast packet, and when it opens it, it will find that there is a multicast packet. So now that will be forwarded by it on to the RP tree, onto the reverse path tree that has been constructed, right. So you can understand this with respect to this example. So let us say this is the source, alright, and these are the two members here. So what is the first thing that would have happened? Both A would have sent A and B would have sent IGMP join message to their respective designated routers. So from here to here it would have gone, and from here another would have gone from here to here. Okay. Now let us say B was the one which first sent a join message. So a star comma G join message will be sent to this router, which would have forwarded that to this router, and from here it would have gone to the RP. Okay. Now when A joins, right, so this router will send this join message, and at this router there is already a star comma G entry that has been made because B wanted to join this group. So since that entry will already be there at this router, this need not be forwarded further, it will stop here, right. So it kind of merges with the already existing entry here. Okay, so this need not be forwarded further, right. So this is what we meant by saying that it will either go all the way up to the RP or it will stop at an intermediate router. Right, so that will be the first process. Once a join is done, from the RP we have the path constructed like this, right. Now the source now will send, we'll have to do a multicast send, and that will go to the DVM, to the DR over here, and this DR, this designated router, will now encapsulate it and send it as a unicast IP packet to RP, right. Now in between there may be multiple routers here that has to go through, right. It will go through all those, it will go to this RP. In this example you have shown a direct link, but it may actually go through multiple routers here. So it will reach RP as a unicast packet. Now unicast now, the RP now will take this unicast packet, it will open it up, and then it will send this multicast packet down this tree. So this is basically the first phase of the PIM protocol, which is the RP tree based forwarding of data. So a quick example again to understand this. So let us say for instance we have a set of routers here, and R6 will be our RP. Okay, let us assume that R6 is chosen as the RP, and now let us have some members in the group. So for instance Alice wants to join a group called G. So what is it that Alice will do? So Alice now, Bill wants to join a message group called B. Okay, so Bill now sends a message saying I want to join this group G. So that information goes to R3. So at R3 now there is an entry that is made which says a state is created saying that star comma G is what it is interested in, right, a star comma G entry, and the out interface for that is set as 1. So it knows that if R3 receives a packet which is meant for star comma G with this multicast address, anybody could be the source, it will send it out on this port 1, so it will reach Bill. Okay, that is what happens at this very first step. Okay, so it comes here. Now the next step will be that R3 will forward this join, will send this will send a PIM join message towards RP. Now RP happens to be the very next link, right. So that information will be stored at the RP. Now let us say John also wants to join this group. Okay, so he sends a join message to R4. So at R4 there is a entry made saying star comma G, the out interface for that will be 2. Okay, and since it sends it out on to R2 via this particular port, right, so in this interface, so it also marks the in interface as 1 and sends it out to this router here, R2. Now R2 will again make a similar entry. At R2 an entry is made star comma G, the out interface is through 3 and the in interface is 1, this entry is made, and join again is propagated towards RP. Okay, so now at RP now we have got 2 joins, one from here and one from there. Okay, so all this information is available at RP. So let us say another person here, okay, Ram wants to join and wants to receive messages from this group. Okay, so now he does a join, sends it to R1. R1 similarly makes an entry star comma G, in interface is 2 and the out interface is 1, and forwards it to R3. Okay. Now at R3 it will stop, there will be no join message sent over here, so which is why I have shown it as a crossed out thing. There will not be any join sent over here. The join will stop with this. Okay. So you will have a final tree which is constructed shared tree, which has RP as the root, and through R2 and R4 you have a path, and through R3 and R1 we have a path. Okay. So this will be the shared tree that is constructed. So now let us say somebody wants to send messages to this group. Okay. So let us say for instance Newton wants to send messages to this group G, which consists of John, Bill and Ram. Okay, Newton is here connected to R7, let us say. So what is it that now he will do? Newton now will send a multicast message to R7, and which is its designated router, and R7 now will send a PIM register message. So this PIM register message will have the source address as R7, destination address as RP. Okay, so this will be a unicast packet, right, which will consist of this multicast packet which has the source address as Newton and the destination address is G. So this PIM register message will be sent from R7 to RP. So now when RP receives this, it will decapsulate it, and when it decapsulates it will find that it is a multicast packet with source address as Newton and destination address is G. So it already knows what to do with the star comma G brackets. So it will now forward it on both the links which are connected to the interfaces 1 and 4, which are connected to R2 and R3. Okay. So now the receivers who are here will now receive this packet. Okay. So RP now can similarly forward the message to Bill, Ram and John. So this will happen along the path that has already been constructed. Okay. So this is what happens in the first phase of the protocol. Okay. So you can see that packets are being forwarded. Now in the second phase, which is called as a register stop phase. Okay. So let us look at what happens here. Now we find that for every packet that needs to be sent by the source, it has to be first encapsulated by its DR and sent to the RP, and the RP has to decapsulate it and send it. So this encapsulation and decapsulation can be very expensive. So to bring down the cost of this encapsulation and decapsulation, there is a register stop message is what is used in the PIM protocol. So let us look at how that happens. So the first step for this is that the RP will initiate a source specific join to S. What do you mean by source specific join? It says that for this source S, I am interested in packets which are meant for this group G. So this information is sent to S, which means you are looking at the RP, which is connected to the rest of the routers who are interested in this group. The RP is now sending a source specific join to S. So now you have a tree which will be rooted at S, and from S you will have a path to RP, and from RP you will have a path to the rest of the members. Okay. So what is the advantage of doing this? The basic advantage is that all the routers on the path, that is from the RP to S, will now record the S comma G multicast state. That is, they are now in a position to forward multicast packets which are meant for G, which are coming from S, and they will forward it from S towards RP. Okay, that is what will be the information that will be set up along this path. So now packets can start to flow following the S comma G tree to the RP. That is, we do not need to do a unicasting or a tunneling of the packet. Instead, what we can now do is a multicast packet which is sent by the source can directly be sent as a multicast packet itself towards the RP. Okay, so that is basically what happens now. So now once that happens, the RP now will receive duplicate packets. That is, it will receive both this native packet and the encapsulated packet. Now remember that until the source is sure that the RP has started receiving these multicast packets, it cannot make any assumption, right. So it will have to make sure that it will still continue to send those native packets, send those encapsulated packets. So until a certain point of time, the RP will receive both these multicast packets which are coming from the source as well as the multicast packet encapsulated in the in a unicast packet. So once it starts receiving the duplicate packets, then it will discard that encapsulated packet. It can just forward the already received multicast packet, and now it will send a register stop message to the DR of the source. So this will tell the DR that it need not send these unicast packets anymore. It can just forward the multicast packets as it is. So with this step, no encapsulation and decapsulation will be performed further. Okay, once this is done, no encapsulation decapsulation will be required. So now the RP can start forwarding the native packets to the RP tree. So it receives it as a multicast packet and starts sending it as a multicast packet itself. So this is the second phase that we have. Now if on the way, if the packet reaches a router with a star comma G entry, you can do a shortcut to the receivers. You do not even have to again go all the way up to the RP. Okay, so this will be another advantage of doing this kind of a multicast, a source specific multicast from the source to the RP. So to look at this example again, so if I have the source here, right, so what happens here is that the RP now, it has already constructed the tree, will now send a source specific join to this. Once the source specific join is sent, that S comma G is sent, now the source, once it sends a packet, multicast packet, that multicast packet will be sent as a multicast packet to RP, and that will be forwarded by RP along this tree. Okay, you can see that the red line here indicates that it is complete multicasting, that is the path of the multicast packet that is sent. Okay, this is basically how the register stop phase will work. Now there can also be a further optimization if required, which is called as the shortest path tree phase. This is the third phase, but this is an optional phase. So the motivation here is that to go from source to RP and then to the receivers, that path can be very long. So if you may have actually a shorter path from the source directly to the receivers, right. So in those cases, we would like to avoid this unnecessary delay. So what we do here is, the steps are as follows. So a receiver's designated router may optionally initiate to transfer from the RPT to a source specific tree. That is, it wants to now construct a source specific tree. So what will it do? It will issue an S comma G join to S, that is a source specific join saying I am interested in this source sending to this group. That kind of a join message will be sent to S, and similarly this join message may reach the source or converge at some router, right. One of these two things can happen. So it starts to receive now 2 copies of packets, because once it joins this, you will also have packets being sent along this tree as well as along the RP tree. So now once it starts receiving packets along the source specific tree, it can drop the one from RPT, okay, and then so how will it drop? When the moment it drops the one from RPT, it also has to get out of that particular tree. How will it do that? That it can do by sending a S comma G prune message to RP, saying that if it is from this source to this group, then I want to be out of this particular tree. Okay, that kind of a prune message, a very specific prune message can be sent. So once this prune message reaches the RP or it converges at some router in RPT, further these messages will not be sent along that particular path. Okay, this is the idea that is used in this third phase. So this will make the whole thing even more efficient. So that's the idea for giving this. So for instance here, a router here can do a source specific join, for this SG for instance, can do a source specific join. So now it is directly connected to the source. So it will directly receive packets from here now. So now from this tree, it wants to get out of this tree, right. So it will send a source specific prune to this router. So this router need not forward the packets anymore from here. Okay, that's the idea that's used in this shortest path tree. Okay. There are also source specific joins and prunes which are there, which are supported as part of the IGMP v3 protocol as well. So how this basically works is that if a receiver sends a source specific join using IGMP v3, and if there is no other receiver on that group, the DR actually may omit performing a star comma G join, a wildcard join. Instead it could do a source specific join. So these are certain optimizations that are available in IGMP v3. And the multicast addresses that are used for source specific multicast are in this range, 232.0.0.0 to 232.255.255.255. So only source specific join will be accepted for groups in this range. A receiver may also send a source specific join with an exclusive source list. Now exclusive source would mean that it is not interested in these particular sources. So in that case, DR will perform a star comma G join as normal, but will also combine this with the S comma G comma RPT prune for each source in the list. That is, it says I want to join this group in general, but not for these sources. So it will prune only these sources out of this particular group. Okay, so these are certain options that are available in IGMP v3. So with all these put together, PIM becomes a very efficient protocol. Now there is also another important aspect that PIM supports, which is support for inter-domain multicast. That is, when you have members belonging to different domains. So then how do we make sure that the tree can be constructed across these domains? That becomes a very cumbersome process. So what actually is done is that every domain maintains its own RP, okay, but the RPs talk to each other, okay, using what is called as a multicast source discovery protocol. That is, the RPs maintain a peering relation with RPs in other domains. So they can talk to each other. Now and what is it that they, what is the information that they exchange when they talk using this MSDP protocol? Is the following. So what they actually do is, when the RP learns a new multicast source within its own domain, it will inform its MSDP peers, that is the other peers who are there. Okay. So the RP now will encapsulate the first data packet that it receives in what is called as a source active message, an SA message, and sends this to all the peers. So this SA message actually is a multicast, consists of a multicast packet which is being sent to the other RPs. So the other RP now, if it has people who are interested in this particular group, will now forward, the other RPs now will forward this message. So this SA is forwarded by each receiving peer using a modified RPF check. So what is a modified RPF check? It will basically check if it is an RP and the RP has a star comma G entry for the group in the SA, then the RP will send a S comma G join. That is, this RP now joins this particular source. So the RP also decapsulates the data and forwards it down its shared tree. Okay, it forwards the data at the same time. It now says I am also interested in joining this particular group, so it sends a message to this source. So once that is done, so the source also gets, this RP also gets connected to a source. Okay, so the receiver that is interested in this S comma G could send a S comma G join to have the shortest path to the source as well. So these are the options that we have. Okay, so once this is done, you will see that data can start flowing through the RPs to the other members who are there in the other domain. Okay. And each RP will periodically send these essays, which include all the sources that are there within its domain, just to inform the other RPs that these essays, these sources are available. So a quick example again to understand this. So let's say this is domain A and this is domain B. So for instance, let's say this is the source which is sending a message. So it sends a register message to RP1 to send its data. So the moment RP1 gets its PIM register message, it will now send, it will join, okay, it can send it down its tree, right? That is something that the forwarding it will do. It will forward it. In addition to that, it now sends a source active message to domain B's RP2. Now RP2 here will see that it has members who are interested in this. So it will now send a join to this SR, okay, to this router over here. So now what happens is, subsequently, now you have a tree which is constructed, which goes from RP2 to SR, right, or other way around, from SR to RP2 and from here down to the members of this domain, and from SR anyway to RP1 and from there to the members of this domain. So you can see that there is a complete tree which is set up, which covers all the domains. So you will have from the requested source to the corresponding RPs which are interested in receiving data from this source, the tree will be constructed, and then along this tree the data can be forwarded. So for inter-domain multicast, we also have support from the BGP protocol, which has been extended to support multicasting, which is called as the M-BGP protocol, multicast BGP protocol. And you have support for IPv4 unicast, multicast, V6 unicast, multicast, and so on. And routing information in this case is carried in some in the same BGP sessions. Okay, so this is what is done for support for multicast in the other protocols that are available as well. Okay. So to summarize on multicast, there are two options that we have. One is a source-based tree and the other is the shared tree. Source-based tree has the advantage that optimal path between sources and receivers can be set up, but the disadvantage is that the routing information has to be maintained for each S comma G pair. Shared tree has the advantage that of less state in each router, but a non-optimal path between sources and receivers. Okay. So with respect to PIM, this is what we have looked at. We have looked at the dense and sparse modes of operation, which covers both the source-based tree and the root-based tree and the RP-based tree. And we looked at how the RP is used, the join and prune messages, how the RPT is constructed, how register and register stop messages are sent. We also looked at how a source-specific tree can be constructed. And we also looked at how the MSDP protocol is used for the inter-domain multicasting. Thank you.